At this point, we've talked about matter and elements. Today we're going to zoom way in and look at what's happening inside the atom. In this lesson, we'll focus on three main ideas: what particles make up an atom, how those particles are arranged, and how we can use that information to draw Bohr diagrams to illustrate the subatomic structure of atoms. By the end of this lesson, you should be able to look at a specific isotope of the element and determine how many protons, neutrons, and electrons it has. So this is Schrodinger's model of the lithium atom. We saw this in the previous lesson. So rather than drawing all these speckles all the time, which would be very inconvenient, instead we're going to define a three-dimensional region in space within which there is a certain probability of finding the electrons that go with that particular energy level. So this is for the quantum mechanical model, and so we're going to use geometric shapes to represent the region where there's a 90% chance of finding the electrons. And we'll see how the shapes of these orbitals depends on what row number you're talking about. So for the third energy level, there's actually 9 sublevels total. There's one of them that's just a sphere that we already saw. There's another one where it consists of 3 orbitals that look kind of like peanuts. They're called p orbitals. They look like they're just the same thing. They all have the same shape. One of them is lined up with the x-axis, another one's lined up with the y-axis, and the last one's lined up with the z-axis. And then we also have a total of 5 d orbitals, which are either lying in the plane lying in a plane, or we have this one special one which is lined up with the z-axis. In the next unit, we'll come back to these and we'll see what all of these different things, what the significance is. All right, so here we have the periodic table of the elements. This is a special one. The only time we really use it is for today. The only thing it has on it is the atomic number for the different elements. The atomic number is defined as being the number of protons. So if you have 1 proton, it's hydrogen. If you have 2 protons, it's helium. If you have different numbers of neutrons or different electrons, that doesn't change what the element is. It's only the number of protons that define what the element is. And if you are talking about neutral atoms, which is what we're going to be doing today, the number of protons have to be equal to the number of electrons, because we have to make sure that we've canceled all the charge out. So let's look at how we arrange the electrons around the nucleus. And so we're going to use Bohr's model for this because it's a little bit simpler to work with than Schrodinger's. So as we saw with Bohr's model, you have different energy levels, and the energy level increases as you get farther away from the nucleus. One of the ways you can kind of visualize it is sort of like a stair step. So at the ground level, we have the nucleus, and there's a big step, a big energy gap to get up to the first energy level. That's where the principal quantum number equals 1, and this one holds a maximum of 2 electrons. And then we have still a big step, but not quite as big as that first one. We get to the second energy level, and that one holds a maximum of 8. And then, again, a slightly smaller step, and it's really important that you notice that these energy levels are getting closer and closer together because it affects the chemical properties of these atoms significantly. So in that one, energy level 3 can hold a maximum of 18. And then another even smaller step for level 4, that holds a maximum of 32. Now don't get too hung up on these numbers because, again, it's just for the Bohr model. Bohr model only works perfectly for hydrogen atoms, and then it breaks down by the time you get to calcium. If you just want a quick reference on how to figure out what these numbers are, the number of electrons is equal to 2 times n squared, where n is the principal quantum number. So for example, let me get my pen going. If you had We're talking about the fifth energy level. N would be equal to 5. So that means that the number of electrons, and a handy-dandy abbreviation for electron is E with a little negative sign on it, so you don't have to write the word out all the time, is equal to 2 times 5 squared. 5 squared is 25. 2 times 25 is 50. So that means that if your energy level is the fifth one, then we can hold a maximum of 50 electrons. All right, so now let's look at how we place the electrons around there. So I call this bit borings aren't boring. All right, so here's hydrogen, and the dark circle in the middle is going to represent the nucleus, and then this dashed line is going to represent an energy level. So there are a couple of different ways to represent specific isotopes or types of atoms, just like you can have different cats that have different colors and different masses and different everything else. They're all still cats. So an isotope would be a specific type of cat in that analogy. So there's 3 different types of hydrogen, and so we're going to specify which one we have. And this one is hydrogen 1. All right, so that bottom number on the isotope symbol, which is what I call this thing right here, it's kind of like, it's a really nice shorthand, tells you how many protons you have. That's the atomic number. The top number is the mass number. Now the mass number is the number of protons plus the number of neutrons in the nucleus. Because you're just counting particles, the mass number is always going to be a whole number. This is why I want you to use the special periodic table, because if you start looking at the regular periodic table, you're going to get the decimal values, the atomic masses that are listed on there, confused with the mass number. All right, so the reason why I like this particular notation is because you can just subtract the 2 numbers, and that tells you how many neutrons you have present. So hydrogen 1, notice we put the mass number after the name. By saying the name, you're saying you have 1 proton. The number that comes after it is the mass number. It is not the atomic number. So we're going to write the number of protons and neutrons in the nucleus. We have a neutral atom, which means that the number of protons and electrons are equal. So we're going to put 1 electron on there. Most of the time, people, oops, I need a pen. Most of the time, people would just put a solid dot on there. You don't put E's in there. I was just trying to make it clear that I was talking about an electron and not a proton or a neutron. So let's go on to another example. Oh, valence electrons. I forgot about this part. So valence electrons are the electrons that are in the outermost energy level. They are extremely important because they are the ones that determine the chemistry that the elements, the atom can do, because they're available to be lost, or you can add some more in there, or you can share them. So that's why we're going to be looking at how many valence electrons we have on our different Bohr diagrams. So helium-4. So remembering that this number is the mass number, and we look at a periodic table and we see that helium is element number 2. We draw our isotope symbol. Say, okay, well, if I subtract those 2 numbers, that means I have 2 neutrons. This bottom number is a number of protons. And we're going to have 2 electrons. So we go 1, 2. Now remember, here we have our energy level, and here's the number of electrons it can hold. So for energy level 1, we hold a maximum of 2 electrons. And you can't get any more to go in there, so that means that one's full. And I'll do a couple more. So energy level 2, maximum of 8. Energy level 3, maximum number is 18. And of course, I put it right where the valence electrons are going to show up. So let me erase this real quick. And there are 2 electrons in the outermost energy level, so the number of valence electrons is equal to 2. So lithium-7. Lithium is element number 3. Remember that 7 is the mass number. So we set up our isotope symbol, do the subtraction, and we see that we have 3 protons and 4 neutrons. When you are drawing Bohr diagrams, make sure you label the number of protons with a P and the number of neutrons with an N. Otherwise, I can't tell if you knew the difference between protons and neutrons. So we have 3 electrons in total. So we do 1, 2, that ring's full, that energy level is full, so we need another energy level. And there's our third one. Notice, if you're looking at a periodic table right now, lithium is in the second row. And the row that an element is located in tells you how many energy levels it has, according to the Bohr model. So we could know right away that we're going to have 2 rings on this Bohr model diagram. Number of valence electrons, remember those are just the ones that are in the outermost energy level. There's only 1. So we have 1 valence electron. So fluorine is still in the second row, so we're going to have 2 rings. Fluorine is element number, I don't remember, element number 9. So I know masses better than I know atomic numbers. So anyway, we just subtract the 2 of them, and we see that we have 11 neutrons and 9 protons. Remember, one of the big discoveries that Rutherford's lab found was that the reason why the atomic masses did not increase at the same rate as the atomic number is because we have different numbers of neutrons present. And so this particular one weighs 20 units. There's lots of fluorine atoms that weigh 19 mass units, so you can see that there is a variation. All right, so we're going to have 9 electrons total. So there's the first 2, so we need 7 more. So we're going to put 7 in that second ring. 1, 2, 3, 4, 5, 6, 7. And when I'm drawing Bohr diagrams, I like to put them together as pairs because it makes it a little bit easier to count, especially when you start talking about the bigger atoms. So we say, all right, well, number of valence electrons, we got 2, 4, 6, 7. So there are 7 valence electrons. All right, so the worksheet that goes with this particular one needs a little bit of explanation. So on one side, we're going to be drawing Bohr diagrams. And on the other side, we're going to just be identifying atomic structure. So let me see, let me put it back on pen. All right, so there's a number of different parts to this. We have to draw the isotope symbol. You have to tell me how many valence electrons it has. You have to draw a nucleus and give the number of protons and neutrons. And you have to have the rings with the appropriate number of electrons. And like I said, you can just have a dot. You don't have to put the little e's in there. So let's go ahead and go on to lithium. So like I said, the row that the element is in tells you how many rings you're going to have. Lithium is in the second row, so that tells us that we're going to have 2 energy levels. So the first thing we do is we write our isotope symbol. So there's lithium. This is its mass number. Because remember, by saying lithium, we're saying it is element number 3. So its mass number is 6. That number goes up top. And when you subtract them, you get that there are 3 neutrons. So we'll try to write this small. So we have 3 protons, 3 neutrons. There is 1 ring. And even when I'm using a regular pen, I can't draw circles. So we have, I'm going to use a different color for the electrons. So there's 2 electrons, and then we got 1 more electron. Let's go on the outside. So we have one valence electron. And then the rest of them are going to be done exactly the same way. You have to write the isotope symbol, number of valence electrons, and fill in the nucleus with an appropriate number of protons. Oops, I just realized I made a mistake. Protons and neutrons. So that should be an N. I'm glad I decided to go over the expectations again. Protons and neutrons, and then you also have to indicate how the electrons are distributed in the different rings. All right, the next part, I call it atomic numerology. Numerology is kind of like astrology, but with numbers. So you can say, oh, your birth date is this, so they can tell all these different characteristics about you based on that. Just another one of those silly things. All right, so just remember, and I'm going to use the highlighter. So we got this bottom number is the atomic number, which is also the number of protons. And these are all neutral, so that means it's also the number of electrons. The mass number, let's use green, is this upper number, the bigger number. So that's going to be the mass number. The thing that most people lose points for on this assignment is they do not add the mass number after the name. If you notice, the cobalt example on here has the mass number given to you. So switch back. All right, so the name with the number is going to be silicon 29. That 29 is the mass number. It is not the atomic number. This bottom number is the atomic number. And then if you want to find the number of neutrons, you can either come over here and subtract, or you can do it up here, say mass number minus the number of protons equals the number of neutrons. So there's 15 neutrons in this case. Now let's go on to the cobalt example, and then I'll let you do the rest. So we have our cobalt. Remember, that's the mass number over here. So we're going to put that up top. We look at that special periodic table and we see that cobalt is number 27. So that means our atomic number is 27, our number of protons is 27, and the number of electrons is 27. Mass number is 58, which means the number of neutrons is 31. Oh, and I meant to put that up there so I could show you that cobalt is number 27, but it's kind of hard to read, so just as well. All right, so that's it for this particular unit. So to wrap it up, atoms are made up of protons, neutrons, and electrons. The atomic number is equal to the number of protons. Remember, that's what defines what the element is. If you change the number of protons, change the atomic number, you change the element. And in neutral atoms, it's also equal to the number of electrons. The mass number is equal to protons plus neutrons, and since you're just counting particles, it's always going to be a whole number. So if you find yourself writing down numbers with decimal values, something's gone wrong. We saw that electrons occupy energy levels, and we have the different numbers. I think I'll write down the numbers again. So remember, they go 2, 8, 18, 32, 50. And then the Bohr diagrams show us how these electrons get distributed. And remember, one of the quick ways you can tell how many energy levels you're going to have is equal to, or the number of rings is going to be equal to the row the element is in. So if you were talking about, let's see, I don't have a periodic table in front of me. Something that's in the third row, it's going to have 3 rings. And then valence electrons, we got introduced to them today. We're going to spend a lot more time on them. The reason why they're important is because they're the ones that are available to participate in bonding. So that's it for this lesson. Thanks for listening.